UTCB, viitorul e al tău, noi punem temelia. UTCB, construim pentru România. UTCB, Universitatea de Construcții București.
Thank you very much. Well, we're usually much more modest as engineers, not as boasting as it's our fault, not Loretta. Thank you very much for coming. Now my presentation will be a little bit more on mechanics aspects rather than strictly code provisions. So you heard enough, I think, from both Professor Loretta Batali and Kyriazis Pitilakis. So let me say that my topic is primarily soil structure interaction, or as we say, soil foundation structure interaction. But also I will touch on the foundation design of the Eurocode, of the new, or actually in the new Eurocode 8. Okay, let me go. First of all, I will start with the mechanics of the problem. What are we talking about that the code is trying to sort of regulate or give advice to the designers, to the engineers? The mechanics, primarily physics, method of analysis, and some typical results. And then I will go a little bit into some clauses of the soil structure interaction, chapter 8 of the Eurocode, which talks about kinematic and inertial response, force-based versus displacement-based methods, rules and simplifications. And then, if time allows me, and this watch doesn't interrupt, I will talk of some aspects of the foundation system, which is very similar to the previous one. We have two separate chapters. I think it's a little bit too detailed for this, but anyway, shallow, embedded, and deep foundation. So, let's start with a basic seismic problem from the geotechnical point of view. We have the structure on the foundation, which is not just a simple spring, as we usually see structural engineers do it, but it's a whole system. Here is an embedded foundation. The waves arriving from the base, not only vertical, all sorts of waves, and propagating through the soil affect foundation and structure as well. We usually, the definition of the seismic hazard, of the seismic motion, is through a response spectrum. Kyriazis talked a lot about it, and this design spectrum may be defined for a rock outcrop motion or for a specific soil, as the new code is doing, in terms of a design spectrum about which I will talk about. And then eventually we have the base motion of the system. Now we like to, conceptually at least, divide the problem in two aspects. One, which is called kinematic response, is the response of the soil and foundation without the structure. This is important. The soil will propagate through and reflect and be modified by the presence of the structure, without any inertia. The inertia comes afterwards, when the structure is starting moving because of the motion of the foundation, and sends its own waves back into the soil. From the sides, as you see here, propagating more or less horizontally, and going down to depth. So these are the two problems, but I will start inertial response, and I will start with inertial response because this is what classical civil engineering is using. We are familiar with this. The inertial forces and the foundation compliance. Now, the inertial response means accelerations on the top of the structure, moving, giving moments and forces at the base, and producing the whole displacement from the inertial response. Okay, now, this inertial response has two effects. First of all, the shear force and the overturning moment, even if the axial force as well, we have frames, but for simplification, usually it's the shear force. Unfortunately for geotechnical engineers, is with the letter V, which we use for vertical, but this is a structural engineer's world, and it is very for the horizontal. I'm not using this in my research, I'm using another symbol, Q, a neutral one, but anyway, V now, where in Eurocode I have to do this, is shear, not vertical, horizontal. Anyway, these are induced into the ground, and then this V&M produce additional horizontal and vertical stresses in the soil due to its flexibility. And this creates lateral displacement and rotation. Now, this is the typical thing. The classical non-soil structure interaction thing is to consider the structure, a simple structure here, on a fixed base, as if it was on rock, on rigid ground. Now, of course, reality is the right one. The soil is flexible, deformable, compliant, this is more appropriate word. And unfortunately, I don't know Romanian to say what is a nice word for this. And even if there is no sliding, there will be horizontal displacement in the ground and will be rocking displacement, and this is a totally new picture. Now, how do we deal with this? It's familiar to use springs, at least, to replace the response of the foundation soil system. Vertical springs, horizontal springs, and rotational springs, with various names. Now, well, this is not only springs, but should be accompanied by daspots, because we have energy dissipated into the soil in addition to deformation, static type deformation, and as I'm sure you know very well. Now, the spring stiffnesses of these things that you see there, it's not only static stiffnesses, they usually vary with frequency. And the Eurocode tries to handle this in a practical way for the engineer, other than say, do a complete dynamic analysis, always. And the dashboards, what are they? Well, they include the usual inelastic material property dashboard, the hysteretic dashboard, as we call it, material damping, but also radiation damping. And you will see something in the Eurocode, this plus in quotation marks doesn't mean algebraic addition, but proper combination. Maybe addition sometimes. All right. Now, this modeling can be done with finite elements, but I will not deal with this at the moment. I will deal with the springs and daspots first. And, well, first of all, the Eurocode, there's also, in reality, there are a lot of nearly exact solutions based on elasticity and finite element analysis for all these values of springs and daspots. For example, for a foundation on a homogeneous soils on rock, as you see here for a circle and a strip. And these values depend on the shear modulus G of soil, of course, the dimensions of the soil, this is for a circle, radius R, and also depend on how thick is the soil layer. This H here is the thickness of the soil layer. But we have to remember at the end of the day that these are only the static stiffnesses, and they have to be multiplied times a dynamic factor, which is a function of frequency. And this presents certain difficulties. So anyway, there are solutions even for, again, elasticity based, for arbitrarily shaped, any shape of foundation, any reasonable shape of foundation, where we circumscribe a rectangle, and through this you can have formulas for the translational stiffness, vertical, horizontal, and in the two directions, horizontal X and horizontal Y, and also for the rotational stiffnesses with the symbol Rx, Ry, or Rz, depending on the characteristics of the foundation. Now, the frequency-dependent part of the foundation stiffnesses is shown here for the vertical stiffness and the horizontal stiffness, and you can see that only for the vertical stiffness there is some significant variation with frequency. And notice also here primarily the dashpot, the damping coefficients which are on the right. The damping coefficients are nearly constant. Very high radiation damping for the vertical motion, which is of little interest in earthquake engineering. Significant damping for the horizontal, but if we go in the rocking, in the rotational modes. Now, the rotational KR stiffness, or the circular, is very significantly affected by frequency in normalized form on the right axis. But the important thing for us is the rotational damping. It's much smaller overall, and it starts from zero. It's very small at low frequencies. And this is the range, if I may show here. No, it doesn't show very well. This one? No, that's all. You can see the small values of damping. This is very significant for our analysis. But anyway, there are, for all kinds of waves, you can see, as we present later, exactly how the Eurocode specifies it. Now, what are the recognized effects of this inertial interaction? The increase in fundamental period, which we all understand, and also the increase in effective damping. The increase in fundamental period for this simple 1 degree of freedom system is very easily obtained having the stiffnesses KH and KR, I call it here, in horizontal and rocking motion. And it's very easy to derive these equations. I'm sure you have seen it in your earthquake engineering classes. It's nothing to determine. The outcome is this: the fundamental period accounting for soil structural interaction versus the fundamental period of the structure alone, fixed base structure. And you can see this can have values up to 2 if the soil is very soft. The denominator of the horizontal axis is how stiff the soil is. And you can see here as a very slender structure with H over B of 5. Of course, it is more affected than a squat structure of 1. Now, this is trivial, but the damping is very important. Now, the damping, the effective total damping of this system has a structural component, which I don't deal with at the end. This Xi that you see here, or Xi, I don't know how you call it, but is the usual 5% or whatever else is for structure appropriate. But this green part is the foundation damping. And it has 2 components: the radiation damping and the hysteretic damping, due to inelasticity of the soil, the fact that the soil is not linear. And of course, it's a function of gamma. I will talk just about the radiation damping, and here is the important thing. This effective damping is significant only for structures which are not slender, squatty structures. H over B of 1. Why? Because the horizontal shearing, not the rotation, is the dominant. And in horizontal shear, the damping is very significant. You remember which I mentioned in the previous one. When it comes to rocking, when this is a very slender structure with H over B of 5, this radiation damping is very small, up to 5 or 6% if the soil is very soft. Very significant to deal with this. And in addition to this, note that these curves, which are in the literature, in the codes, are for homogeneous half space. Now, homogeneous half space may be good for stiffnesses, it's not very bad. Is it for damping? Not really. The presence of stiff layers in homogeneity or the presence of rock nearby very significantly affects and diminishes this damping. And I have here 2 examples. One is unfortunately from a publication of mine, homogeneous versus inhomogeneous soil. Inhomogeneity being in terms of a linear increase of stiffness or square root of stiffness variation with depth, very significant, very appropriate for soils. Even a homogeneous, even a uniform soil, sandy soil will have a shear modulus varying with the square root of depth, not being constant. And you can see how these values diminish the rocking damping. And more significant, if you have rock, what does rock do to damping? May not do too much for the stiffnesses, but for damping it's very significant because the waves emanating from the soil, especially in the horizontal mode, even in rocking, they will be reflected in the rock and return back. So there is no radiation damping, no loss of energy because of waves propagating to infinity. So it turns out that below the fundamental frequency of the soil, there is no radiation damping. And this is what I very simply show here. Below F1, in terms of frequency, there is practically no damping. This is an idealized curve, it's not an exact curve. You'll see a better one later, and have it in mind. But now, the conventional consequences of soil structural interaction. With the usual spectra, which have been derived by this probabilistic analysis, which Kyriazis mentioned that I don't like very much, for determining the design spectrum. And I'm sure people in Bucharest will agree with me in this. But anyway, the classical thing is, as the period increases from T to T soil structural interaction, or T with this hat there, this tile over there, you will invariably move to lower values of spectral acceleration, especially if damping increases as well. Instead of the yellow curve, you have this turquoise curve, blue curve, and it seems that the decrease in base shear will be always the case. But of course, at the same time, the displacements are increased because displacements are proportional to period squared for a given SA. But anyway, but these code spectrums imply that SSI is always beneficial. And that's why most people have ignored it for so long. But reality contradicts this. And of course, in Bucharest especially, this is definitely the case. Look, many other earthquakes, the spectra do not conform with the code spectra. Of course, Mexico City is an extreme case where the fundamental period of the soils have a tremendous influence, but you know very well in Bucharest from the Francia earthquake, which is respected in the code, fortunately. I'm so happy to see this. Some years ago I realized it. How can you say that soil structural interaction, by increasing the period, things are better? Can be much worse. Have this in mind. I will not deal with it anymore. Now, I'm going directly to the kinematic response, which is also very significant for two reasons. First of all, because the kinematic response modifies the ground motions. The foundation input motion, as we call it, can be very different because of the presence of a rigid foundation, a bended foundation, or piles. I will show you some examples. And also, these embedded foundations, unfortunately, they have to pay something for this. They will be subjected to additional distress, especially piles and basement walls, or simply retaining walls will be subjected to additional distress. Actually, the basement wall, the retaining walls are designed for kinematic effects, not from the load from the superstructure, which they usually do not carry. Anyway, this having in mind. So don't read this, just look at this Mickey Mouse sketch that I have there, the waves coming upward. Obviously the foundation, an embedded foundation, which is more or less rigid, even if it's flexible in structural terms, cannot follow this detailed motion, and it distracts this motion. And I have here a very simple-minded. This is for teaching in the class, not really. You know, if you think of the soil, free field soil, as being an upward harmonic wave, this harmonic wave will have the following distribution, the one you see on the right. U0, which is the motion at the top, cosinus omega z over Vs, omega being the natural the soil frequency of the wave, the circular frequency, the circular frequency, 2 pi over period, or 2 pi times f, in case you have forgotten, times the depth divided by Vs. This is a simple-minded, one simple wave. Now, can this rigid structure follow this? No, we will go somewhere on the average. Simple-minded analysis. Let's take the average, and this will be the foundation motion. This, as I said, is teaching in class. This integral of this divided by the depth, average over the depth, in other words, you will give the ratio of foundation motion over the U0, the free field motion is this, and this is plotted like this. Now, of course, a more realistic analysis doesn't go all the way down to 0, it stops somewhere here, but this is what the more informed spectra look like. They're not, now this is in terms of period. Unfortunately, in dynamics we used to work in frequencies, but now engineers, we like periods. So it's inversely that. So the curve, the right curve here corresponds more or less to the blue curve, and this cutoff that I saw here, 0.45, looks like this. But this is significant. For a bended structures, this is a very significant reduction in effective input motion. Makes a great difference if you take into account. And now I have another example from numerical analysis. The free field motion compared to the motion of the base. They are very different. And I have here the ratio of displacement from an exact analysis, elastic analysis, UD over UE, and you see here in terms of frequency, very much the curve that I found at the beginning with the simplified motion, but of course, after a certain frequency, it doesn't go to 0, it oscillates, but at the same time, there is an imposed rotation. This is regardless of the superstructure. This is just the free field motion only. Okay, now, how about piles? Now, piles, of course, they will modify the free field motion. They cannot follow the detailed motion of the ground unless the period is very large and the wavelength is very large and more or less forms. And I have here an example from some early studies that I did for an inhomogeneous soil in the pile, and of course the motion at the top of the pile follows more or less the initial curve that I saw before with this simple idea of averaging the motion, which convinces the students at least that this is what is happening. And all right, so this is the story. Now, in terms of period, some recent results you see here from Cesaro and Di Laura, two Italian guys, who use actual time histories in the piles, and you will see the same thing. The motion at small periods, less than 1 second, being almost 0.5. You may not think this is significant, but it can be very significant reduction for pile foundation. And of course, at high periods, there's not much difference. Now, however, there is something missing in Eurocode. It is mentioned only briefly, the so-called base slab averaging. It is for large dimensions of foundations. Not for isolated footings far away from each other. The waves, we think to consider of waves going vertically upward, but there are also inclined waves. And inclined waves, and can be incoherent waves, but let's see, inclined waves, as the wave fronts are coming, you understand, the left part of the foundation will be hit first before the last part of the foundation. There will be a phase difference in motion. And the phase means the foundation will be pushed to the right on one side and to the left on the other side. Now, a matte foundation or a raft foundation in the horizontal direction is very, very rigid, stiff. Nobody will compute horizontal displacements of the raft. It's not bending, it's horizontal displacements. And it cancels out these motions. It filters out the wave propagation. As a result, there is this base slab averaging of spectral accelerations, which you can see for very long foundations, 100 meters or even more. It can be also an additional reduction. This has nothing to do with abandonment. This is for surface foundations. Just because of their size, you're allowed to use a reduction on the input motion. All these things, abandonment, piles, and base slab averaging can have a diminishing effect. What is not very well understood yet, there's not much studies, is, before I say that, the penalty to pay this for piles and other things is they get some lateral loading. So regardless of the superstructure, the piles will be subjected to lateral loading. And they have to be accounted for this. This lateral loading increases the moments, of course, at the ground, at the surface, but also at the depth, at the interfaces of different soil properties. And of course, this has to be ended, in quotation marks, to the forces that come from the inertial response, from the structure. And I have here one example, because this interface motion has been even in the previous code. And to impose something in the code which is unusual, you have to have case studies to verify it. We had a very significant case study from Japan of a bridge with 64 piles, a regular bridge, nothing special, passing through very, very soft soil. Now, very soft soil, you can see here the properties, SPT is close to zero, and very, very small shear wave velocities. Now, what do you expect? We had measurements of axial and bending moments. Axial moments, no difference with depth. Why? Because the load coming from the superstructure, the inertial loading, did not diminish at all, because the soft soil did not impose any shear tractions on the soil. It went all the way down to the depth. But the bending strains, a totally different story. The bending strains from the superstructure diminished very rapidly with depth, but then all of a sudden, at great depth, increased. Very much so, that's what happened, as the kinematic soil structure interaction shows it. You can see here the dots are the measurements. The measurements, of course, don't distinguish where they come from, kinematic and inertial, but the inertial analysis, the simple inertial analysis with springs and dashboards, predicts very well what is happening at the base, at the interface between the very, very soft soil and the stiffer soil at the base. And this is the convincing point why the Eurocode suggests that the interface between two different stiffnesses has to be accounted for. Now, not well understood, as I said. Deeply foundations and multi-story basement on piles. And I have an example from Bucharest. I don't show the superstructure, which is a 12-story building next to a famous Catholic church here, 7 meters away. And it is not very clear how to do it other than do a numerical study, and I'll not say anything about it. This is not a well understood problem, internationally speaking. Anyway, so, now, the method of analysis, I will go through it very crudely, and I come here to the Eurocode. Now, how does the Eurocode represent all these phase things? Well, some things are very simple. First of all, the Eurocode distinguishes two different approaches: force-based approach and displacement-based approach. Very significant. Force-based approach is what the civil engineer is used to. It's basically a pseudostatic approach. It's really what we are doing every day, engineers. And it's comparison of forces. The demanding forces should be less than the resistance, or the resistance should be higher. Very simple. This is what everyday practice is. The displacement-based approach is really a dynamic time history analysis. And the distinguish is very clear. The code is very strict in the first part and very liberal, if I may say the word, on the second part, where only displacements at the end of the day are compared. Now, I will not say this because this will say one important thing. The effective ground acceleration, which we're using in our analysis. First of all, the acceleration is good with the Latin A of h, and the Greek alpha is used for the dimensionless divided by h, basically. But now, the important thing is the effective ground acceleration, the way that Kyriazis has mentioned how we define it. God knows how you can find it with all these details, but anyway, you'll find it. But for the design, we don't take it. We divide it by XH, which for a force-based, the conservative pseudostatic approach, we divide this by a coefficient which is a function of how much displacements we are allowing, how much displacement the structure can undertake, and how much we allow it. For example, for retaining walls, you may very well know we divide by 2. We don't take the peak acceleration, that's where the 2 is. And here is a chart, depending on the displacement for footings, it can go even higher than this, how you decide on this height. But for the detailed displacement-based approach, there is no kind. You do the exact foundation, you do the dynamic analysis, and at the end of the day, you compare displacements. Now, anyway, a few more other things. Now, the inertial and the kinematic effects are mentioned very clearly, as I mentioned before. And, I'm sorry. Okay. Now, where else do we use it? Can we avoid? An important thing for engineers are asking. So, the code is really trying to help, essentially, the geotechnical engineer doing the analysis. Do we always have to take into account soil structure reduction, or we can avoid it? No, for Bucharest, forget it. You have to take it into account. Because when it is mandatory, when increasing the fundamental period increases the spectral accelerations. Only for very tall buildings, 20-story or more in Bucharest, you don't have to take it into account. But then, such important structures, you will take it into account because the displacements are important. Anyway, when displacements are important for joints separating, when the structure is founded on very soft soils, when P-delta effects for tall structures are very important. So in these cases, you should. So the idea of this part of the codes are to try to help the engineer to avoid some of these. Kinematic effects. Do we always have to take it? No, if you don't want to reduce your motion, but if you have piles, in case of deep foundations, you have to account at least for the additional moments at interfaces and at the top that the kinematic effects are producing. The retaining walls, unavoidable. Only the kinematic effect that is imposing. So if you have an embedded structure, if you have abutments of bridges, or very large foundations, as I mentioned before. So the idea of this part of the code, which continuously runs like this, is to help. I will not talk about the flexible piles. This is very typical. Now, the inertial effect. The code just suggests using the elasticity-based solutions. It says that we have 6 degrees of freedom in general, and the annex is presenting simple elasticity-based solution for horizontal rocking and coupled horizontal rocking mode for the piles. Do you use this easily? Well, you have to use a proper Young's modulus, not the elastic small state Young's modulus which you get from a VS analysis. You have to take into account the unavoidable nonlinearity and take a strain-dependent modulus. The same thing for the footings. Now, with the damping, the translational modes have very significant damping. Rho, VS, A. It's the last damping which will be undercut by the presence of a stiff layer or inhomogeneity. The radiation damping, this is what the code is giving, and other curves like this, suggested codes. Now, the important thing, what does the code do? Just give this analysis which you can find in textbook? No. Where can we use frequency independent? Guys, we cannot do dynamic time history analysis. Frequency dependent stiffness. Yes, you can use it. But at what period? At the period of the fundamental mode. Totally clear with you. The fundamental mode of the soil. Natural period. If you cannot find this fundamental period, use the static stiffnesses. So, simple ideas like this continuously write in the code if you try to read it. Of course, equivalent linear stiffnesses, as I mentioned, should be compatible with the strains. This is what the second thing is mentioning. Now, in the first force-based approach, the simple approach, forget about damping. We're doing pseudostatic. Pseudostatic and damping, radiation damping, don't mix. Other than this, radiation damping should be used only limited to 20% damping if you have, unless you have done very proper detailed analysis. No, in the displacement-based approach, you can use all kinds of non-linear inelastic sprints or finite element non-linear analysis, of course. And it is, as I said, quite liberal. Uplifting and slippage of the ground is allowed. It's not a restriction of how much the soil can uplift. So they may be included in the model. Now I mentioned this, the high frequency and the fact that the frequency below the fundamental frequency of the soil should not be accounted for. And now this is an interesting thing. Modeling the kinematic effects, you can model it as part of the whole structure, foundation soil system, or a separate analysis, kinematic and inertia. Winkler model can be used, finite element or finite difference models can be used. These are rather trivial things. This is an important thing. How do we combine this plus in quotation marks? This is what this thing shows. How do we combine inertial kinematic effects? Now, usually it says we combine it, see the A aspect there, with the square root of the sum of the squares. We do not end them algebraically unless a special condition is satisfied. This is important because, especially at the top of the piles, you may have very, very large inertial and kinematic bending moments. You do not end them algebraically, but you combine it with the square root of the sum of the squares. Now, when I go to foundation system, they're more or less the same things. I will not go into details of this. Let me move a little bit forward and show only the more important things. Now, it says sliding. Now, we all know this. When it comes to moment creates an axial force. What is the problem? The bearing capacity. Now, for verification, the suggested in Eurocode code, in the Annex E, is an envelope in 3 dimensions that you see here, a failure envelope. But I would say using the classical theories of determining through the Terzaghi coefficient, let's put it like this, is good enough. In case you haven't come up with what is this 3-dimensional surface, I have a 2-dimensional version, ultimate capacity versus N is curves like this, which depending on N and M and the shear, you can find out the ultimate capacity of the foundation. I'm not geared with this. Rotational failure mechanisms, now that's important. In displacement-based design, uplifting and rocking is allowed, as much as you wish. In fact, our recent studies, of the last 20 years, show that it's better to have a lot of uplifting. It benefits the superstructure a lot. But in force-based design, things are very strict. Only 1/3 of the uplift of the area of the foundation should be uplifted, meaning an eccentricity, a dynamic eccentricity of about 1/6 of the base. And and the pile foundation is the same thing. Battered piles. And why do you say they inclined piles? In previous codes, they were very strict, they were forbidding actual battle piles for whatever reason, because they thought the axial forces are very significant and they will create buckling. Now we have abolished this idea, but still battle piles should account for the additional loading from the gravity, in addition to what comes from seismic action. And now another final important thing. When we have pile groups, the cap base, the base soil interface, we have a pile group. Do I count for the shear that the mud foundation is exerting? This can be extremely helpful, but we don't believe it is acting. Now the code is very strict. It says no contribution for this code that if the distance between piles S is less than 6 diameters. I think it's a little bit too much, but people, even at 3 diameter spacing, which is very close, they usually account for the base shear, but the piles being there will not allow the soil to transmit much of shearing action. So anyway, in force-based design, the other thing is the passive resistance should be limited to 30% of the maximum. We're not allowed in an embedded foundation to transmit the forces with passive resistance. Only 30% of it should be accounted for, because it needs a large displacement to arrive at the passive resistance. With a displacement-based approach, find out what is the displacement and whether it satisfies it or not. But anyway, finally, kinematic analysis should give the bending moments not only at the pile head, but the interface between layers of different properties. And there are certain advices of what to do if you don't do the analysis when you have interface with properties vastly different, how to reinforce the concrete above and below the line of the interface. So there are some practical advices, but this is the basic idea. And finally, do we allow plastic hinging of the concrete elements, the strictly foundation elements we call? No, we don't allow much of structural damage in the footings, but in the piles we have restricted this. We have actually made this a little bit more unconservative. We do allow some yielding of the piles. Why? Because we found out from analysis, actually originally from the late Professor Priestley, that because of the presence of the confining soil, the yielding of the piles is not, plastic hinging is not as concentrated in a single point as in columns. So it's much more distributed. And because of this, the rotation is not very significant. So we do allow inelastic responsive files, provided of course that the outcome of displacement is allowing that. So inelastic responsive piles also may have a beneficial effect, like the inelastic response of the foundation and the uplifting of foundation. So that's the idea. I don't know, I went a little bit fast over the codes, but the basic idea of the code is trying to be as scientifically correct as possible, but at the same time giving continuously advice for simplifying methods and simplifications for the practical design, when it is not necessary to do a complete three-dimensional dynamic analysis, non-linear of everything, which of course 20 years from now, 10 years from now, may be the easier thing to do. The code may say, okay, just two lines of code should be, and that's be enough. And with this, thank you very much for this. I rushed a little bit, I apologize at the end of the day, but you got the basic idea of the code, not the details. Okay, but I'm here for questions, written or oral, if we may have at the end of the day. Thank you very much. Va mult mesaj.
UTCB, viitorul e al tău, noi punem temelia. UTCB.